Now we're recording. Now I can share. Share. Yes, now we're recording. All right, so what I decided to do, and this is basically what I had planned on doing anyway, was start with something really straightforward, but will tie up a lot of what we're doing this term. And that is start with a section on series. So how many people have done a lot of work with infinite series? Raise your hand. Okay, great, awesome. This is not entirely useless then. So let's see if this works. This is what we'll start with. And so first off, can everybody see that okay? Yeah, thumbs up, all right. And is the pen noise too loud? Because I'm ordering a headset. Can you hear my voice okay? Yeah, okay, awesome. All right, so we're starting with chapter 1. Why not? Because it's the easiest part of the book, I think. It's still opaque. Did everybody get the textbook? A version of the textbook? Okay. Awesome.
For me.
So we'll start with infinite series, and we've already looked at some of this. If you think back to, say, Comp Mech, you know that we developed a Taylor series and binomial series. We're going to look at infinite series and how we test for convergence and then apply that to a series of functions, and then eventually get to things that we've already seen in like electricity and magnetism and quantum, like Legendre polynomials and so on, spherical harmonics, those kinds of things. So we'll start with some definitions. And the first is our definition of a partial sum. That is, we're assuming that we have a sequence of numbers, and for any of these series, whether they're divergent or convergent, we can define a partial sum S sub I as the sum of terms from n equals 1 to I of U sub n. That's all well and good, but what we're really after a lot of times is a series that converges. And the best way to think about convergence, obviously, is that the total sum is finite. So we can define the total sum S basically as the limit from I goes to infinity of S sub I A sub 2. Now, actually computing these sums is a little tricky, usually involves some kind of mathematical induction. But we'll see that there are a couple of cases that are particularly important. And what we're using this for mostly is to see if something converges. And then obviously we have divergence, right? And that's when S goes to infinity. And a special case of a divergent series, and that's the oscillatory series. That's where you would have alternating positive and negative terms. And one of the things that we're going to be looking at is whether something can be convergent either absolutely or in terms of its values. We can see, if you've done the reading, you know that you can have an alternating series that converges, but if you take the absolute values, obviously they can continue adding up and not converge. So, everybody fine with that speed? Okay. And I've got my eye on a chat window, so you can always, I think what I've done is turned off the chat between all of you all so that you're not passing notes in my class. You can't throw airplanes in this class to each other. But if you need to get a hold of me, then I've got this on one of my screens. So anyway, let's look at some examples. And here's where I may be doing some stuff that the book does, but if you've read through some of the book, you'll notice that Arfken is, well, Arfken, Weber, and Harris, but Arfken well before the other two, was infamous for skipping out steps, leaving out steps. So we'll start with the geometric series. And so we'll consider S sub n is equal to a plus a times r plus a times r squared plus a times r cubed, and so on, because of the way we've defined it to r to the n minus 1. And in this case, if we look at the partial sums, then we've got obviously S1 is equal to A, S2 is equal to A plus AR, or we can write that as A times A, or times 1 plus R. And then S3 is that, right? So if we want to compute, say, the nth partial sum, one way you can go about that, so, is to multiply R times S sub n. Right? Then you get A sub R plus AR squared plus AR cubed on out to A to the R, A times R to the n. And then we subtract that from S sub n. Right? So that means that we are basically subtracting off this term from that term. Obviously, that means that these terms go away, and you're left with A times R, or A times 1 minus R to the n. So S sub n is equal to A times 1 minus R to the n divided by 1 minus R. Okay, so that's the partial sum for the geometric series, right, where A again is just some constant. And we haven't defined anything about, or well, either A or R, right? We're looking at now, if we want to find the convergence, what happens in the limit as n goes to infinity, right? So S then is equal to the limit of S of n goes to infinity, just the limit of n goes to infinity of A, some constant, times 1 minus R to the n over 1 minus R. All right, so what's the condition for convergence here? When does this series converge? Oh, I see. You can speak up. There's my chat window disappeared. Sorry. All right. When does this converge?
R less than 1.
Right. So we have convergence for absolute value of R less than 1, because if that's less than 1, then this term, right, goes away, and we have S is equal to A over 1 minus, no, this should be a 1 here, 1 minus R. And divergence for R greater than or equal to 1. Okay? All right. Next, we'll look at the harmonic series. And the reason why we're doing these two series first is because they're going to be useful in terms of comparison tests, and they're also things that we see all the time. So the harmonic series is the infinite series from n equals 1 to infinity. 1 over n. So that's obviously 1 plus 1/2 plus 1/3 plus 1/4. Okay. So is this a convergent series?
No.
No, no. Why not? How do you know?
I know because it's famous. I don't remember how to prove it.
Okay, that's fine. One thing that we can consider is, one necessary but not sufficient condition for convergence, right, is that the limit of these terms goes to 0. That is, they are monotonically decreasing, right? And that's certainly true, but it's not necessary and sufficient for convergence. So while this looks like it can be, we can consider an alternate series. So consider the series 1 plus 1/2 plus 1/4 plus 1/4 plus 1/8 plus 1/8 plus 1/8 plus 1/8, and so on. And obviously, this is a half, this is a half, this is a half. And the reason why, and I think it's obvious that this would diverge if we do this through an infinite number of terms. And of course, this is not something in which each successive term is monotonically decreasing. If we regroup, though, let's give this a 0.4. Regroup a 0.4. Then the sum from n equals 1 to infinity of 1 over n can be written as 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8. So all we're doing is taking the same couple of terms or number of terms, and this is obviously greater than 1/2. This is greater than 1/2. And so this is like 0.6, this is like 7/12. So this suggests, sorry, this is not. One way of determining whether something is convergent or divergent, that is, we can compare it to a known series that either converges or diverges. So we have then the comparison test. That is, we can compare a series to either the geometric series, typically. We can use others once we know others, and the harmonic series. And we can do that term by term. And if term by term is less than the geometric series, it converges. If term by term is greater than the harmonic series, it diverges. Okay? But that's kind of a blunt instrument and not going to help us with a lot of these other series. So we're going to develop, and your book develops a few other tests that we'll run through. Any questions before we begin with those? All right. I want to give you enough time here. Please let me know if I go too fast with this. I know I've only got one screen, but all right. So the main point of the first part of this was just to define what we're looking at. The second point is to find out which how we can tell if something converges. And then after that, we're going to look at applications. The applications are what we're really interested in. there are physical applications, obviously, and you've used them. There are also some mathematical applications. If we can represent something that looks complicated, but we can represent as a series, then potentially, especially if it's a power series, we can integrate that or take the derivative of that function a lot more easily. So we've already looked at a couple of these. So the preliminary test is just the monatomic decreasing test, right? If your series doesn't pass that, then it's divergent and you can move on. The next is the simple comparison test. But again, there are series in which you can get an indeterminate answer. Then we can look at a couple of other comparisons. I'm going to focus on a couple. We'll start with the Cauchy root test, or not the Cauchy root test. I'm going to skip that one. Ratio test. Right, so all the ratio test does is look at the ratio of one element in the series and compare it to the previous one. In other words, you take the limit as n goes to infinity of two successive terms. That is a sub n plus 1 over a to the n. And if that's less than 1, we know that's convergent. If it's greater than 1, it's divergent. And if it's equal to 1, we don't know. So this obviously has wider use than just a simple comparison test or a preliminary test. But there are cases where it fails. So for example, let's look at examples. If we look at the series n divided by 2 to the n, ratio test of that as n goes to infinity would be the ratio of n plus 1 over 2n plus 1 divided by n over 2n. And that equals the limit of 1/2 times n plus 1. And as that goes, as n goes to infinity, the n terms cancel, right? And that equals 1/2. And so this is an example of a convergent series. On the other hand, we can take something that we know diverges, 1 over n. We take the limit of n goes to infinity. Of this, we have 1 over n plus 1 over 1 over n, right? And that equals the limit of n over n plus 1 equals 1. We can't say anything about that, right? Which suggests we have to use something more powerful. And then you can look at, say, 2 to the n over n squared. If you try that, you should get that this diverges. In fact, it's pretty easy to show that the result of that is 2. Okay, and for my money, for most of the stuff that we do, when you're looking at simple series, this is the series test that you're going to use. You will see some other tests, especially when we look at recursion relations, where we want to look at Gauss's test, which is will come up in a couple of minutes. Okay. All right. So that's the ratio test. You see people are still writing, so I'll take a drink of coffee. Only coffee. Okay. Okay, so go to the next test that I want to highlight. And that's sometimes it's credited to Cauchy, but it's also credited to Maclaurin. That's awful, that's an A. And that's an integral test. So the idea behind the integral test is, again, you have a monotonically decreasing series. But the idea is that if you can translate that into an integral and the result of the integral is finite, then the series converges. So what you should think about, for example, is say 1, 2, 3, this is your n-axis. And then since we're looking at monotonically decreasing values, and so on, you might have a function that looks like this, right? And what you're doing is defining y as your a sub n. And so the idea behind this then is the series, no, Siri, no, sorry. The series n to infinity of a sub n converges if the integral to infinity of a sub n dn is finite. And what's important here is just evaluating it at the upper interval. I think your book evaluates it from 1 to infinity, but that's not actually important. What's important is what is the value of the interval at infinity. Example, the harmonic series, a sub n equals 1 over n. So that's monotonically decreasing. Stop. But if we take the interval, obviously, and evaluate it at infinity of 1 over n dn, that's equal to the natural log of n, evaluate at infinity, and that goes to infinity, so that's divergent. Another example, let's look at which one to use. The sum of n over n squared minus 1 squared. Okay. So here, we translate that into an integral, n dn over n squared minus 1 squared. We let u be equal to n squared minus 1. du is equal to 2n dn. And that means that 1/2 the integral to infinity of du u squared equal to minus 1/2 times 1 over u, evaluated at infinity. And since that's a finite number, it's fine if it's 0. That means that this is a convergent series. Okay. Everybody okay with the integral test? Pretty straightforward. Right? Let's see. Next. And I promise you we will get to applications. But this is hopefully laying down the groundwork in kind of a low risk setting. Kummer's test, I'm going to misspell that horribly just by my handwriting. Kummer's test. Do you know what Kummer's test is? What we're doing here? No? No, it's okay. It's the beginning of the term. Technically, it's the second week of term. I know. I don't know how I'm supposed to do this with 9 weeks, but I'm a trained professional, and this isn't just coffee. So what we're going to do is consider a series with positive terms u sub I. We're going to have basically constant, and we're going to look at the functional form of n. Right? So in all of these things, we've had some constant times n squared or n factorial or 1 over n squared. And what we're doing is taking a sub n times u sub n over u sub n plus 1 and subtracting from it the value of a sub n plus 1 such that it's some number greater than c for any value of n, and that's greater than 0. So if this is true for all n, so if for all n greater than or equal to some large number n, the series u sub I, Siri, stop it. Thank you. Converges. Right. If, on the other hand, it's less than 0, so if essentially if this sum is less than 0, I'll put this in brackets, this diverges. Again, all we're doing is we are taking finer and finer ways of looking at what each next part of the series looks like and what we can discern from that. And essentially, if a sub n is equal to 1, even though this looks a little opaque, but if that constant is equal to 1, this is essentially the ratio test. So this is just a refinement on the ratio test that we started with at the beginning.
Sorry, just again. So a of n is the series.
U sub n is the series. A sub n is the constant that goes in front of the series. I'll show you an example of that. So there's an independence.
Is a sub n different from a sub n plus 1?
Yes.
Okay.
Yeah. So here, let me show you. I've lost my. Hang on a second. All right. I know the book isn't quite clear on this, so let's look at an example. The sum from n equals 1 to infinity of 2 to the n over n squared. Okay, so in this case, a sub n is 2 to the n, and u sub n is 1 over n squared. In other words, u sub n is the power law that's attached to this. In a sense, the denominator. So
is it necessary to be not convergent or convergent, or doesn't matter what series a sub n takes?
No, so all that matters is whether this relation is true.
Okay.
Yeah. So if we look at this and we use this test, what we have is 2 to the n times n plus 1 squared over n squared. Right, so we're looking at the ratio of this times a sub n minus 2 to the n plus 1. That's a sub n plus 1. So then that's 2 to the n of n plus 1 over n squared minus 2. And once n gets larger than 2, this value becomes 0. So one of the things about these tests is that you may have to look at a particular, get beyond the first part of the series. So once you get beyond n greater than 2, this is less than 0, this is a divergent series. And the reason why you would use this rather than something else is that you get an indeterminate result from other results. You can also use this series to find out how many terms before you have before you determine or where you determine that convergence. I think if you look at another example that you can play with, the sum of 10 to the n over n factorial squared. Okay, so in this case, a sub n is equal to 10 to the n, and u sub n is equal to 1 over n factorial squared.
Are those two definitions arbitrary, or could you swap u sub n and a sub n and it would still work?
No, they're not arbitrary. So a sub n would be the numerator. Yeah. And that's why when you go back up here, if a sub n is equal to 1, that's you get back to the ratio test. Good.
So like on the top a little bit.
Yep.
Like when you tell that a u sub of I converge, wouldn't be then be a sub I divided by u sub I converges?
Say that again.
Like in a part right below B3, you're writing that u sub I is convergence. Some wouldn't be then a sub I divided by u sub I converges?
Okay, so we're looking at, so I guess maybe I should back up a little bit. The definition that we're using here is the series has positive terms, and I can see where this might be confusing, so thank you. So we're considering it has positive terms, u sub I, and a sequence of finite positive constants, a sub I. So we're really trying to test whether that that's our definition of our series. The constants themselves are added on as a sequence on top of the series. Does that make sense? I realize this is a little bit confusing, especially since this is gone over in a book in about 2 pages, which is not which is typical for ARFCAN. Okay. Okay, so I'm going to go back here. So we have this for Commerce test. I'm not going to go into too much detail about this, but you also have something that's related to this, which is Rabe's test, which is Kummer's test with a sub n equal to n. All right, so just like when a sub n is equal to 1, you get the ratio test. The Rabe test is a special case of that. And there you're looking for a value where you get convergence when the values are greater than 1, divergence for less than 1, and if it's equal to 1, we don't know again. But that's a special case. All of this is leading to, I think, what's going to be really important for us when we look at things later in the term, like Bessel's functions and Hankel functions and Legendre polynomials and all of those Chebyshev polynomials, all of those expansions that we use for solutions partial differential equations is Gauss's test. So Gauss's test is a little bit different. And here, again, we're basically taking something like Kummer's test or Rabi's test, but we're assuming that the constant sequence on the series is, oh my God, stop it. Sorry. I don't know if you can tell the series keeps coming on or not, but okay, that'll be fun. All right, is n log n. Okay, so definition. If u sub n is greater than 0, so again, positive series for all n, we have the ratio of u sub n over u sub n plus 1. So a little bit different from the other cases. And we can write this as 1 plus h over n plus some function b of n over n squared. And I forgot where we are now already. Okay, mixed up. All right. This is going to be our test. And b of n is a bounded function, hence the b. Of n, or n goes to infinity, then the sum of u sub I converges for h greater than 1 and diverges for h less than or equal to 1. So it'll give you a definitive result. The issue is, can you make your sequence look like this? And you can't always, but the real power for this, where this comes in, is when you have recursion relations. So a recursion relation you've probably seen, well, I know you've seen in E and M. The recursion relation for the Legendre polynomials. If you know the first Legendre polynomial, you can get to the second one and the third one and the fourth one and so on. Right? So in fact, we'll use that as an example. So I don't expect that you remember what the series recursion relation is. I'd be really impressed if you did. I don't. But when we start talking about these infinite series for solutions of partial differential equations, we're going to rely on these quite a lot. So if you think about, and this is a good way, Yuri, I think, to get to your question about what are A's and N's, right? If you think about what the Legendre polynomials are, right? They are series of with constants attached to them. So we can write the following. That is the ratio of 2j plus 2 to 2j, sort of alternating along the sequence, is equal to 2j, that's 2j plus 1, minus L times L plus 1 over 2j plus 1, 2j plus 2. Okay, so that's just the definition of the recursion relation for the coefficients for the Legendre polynomials. And what we're going to do is well, actually, for the Legendre polynomials, let's identify this as our series. And we're going to let u sub j be equal to a sub 2j. Since these are subsequent elements in the series, what we can do is identify from this sequence b of j is going to be equal to terms that are greater than j squared, which goes to 0 for j goes to infinity. That means that b times j squared is going to be less than b of, let's see, j times j squared be less than some number c. And if we use the test, that is, we take the limit of n goes to infinity of n times 1 plus h over n plus b over n n squared minus 1. That equals the limit as n goes to infinity of h plus b over n, b of n over n, and that equals h. Now, in order to make this useful, if we assume enough terms, that is, assume that j is much greater than L. We haven't defined what L is, but if you go back, you realize that L will have something to do with the symmetry of the problem. Then u sub j over u sub j plus 1 goes to 2j plus 1 times 2j plus 2 over 2j plus 1. This is equal to 2j plus 2 over 2j. That is equal to 1 plus 1 over j. So while this is the sort of the general form, if we look at the particular case in this series where we're looking at the ratio of the two terms and we're ignoring the L term, this now is R1. This is our H over here, right? Our function in terms of B is dropped off to 0 for terms larger than 1 over j squared. And so we have H is equal to 1. And not surprisingly, the Legendre series actually diverges, right? And if you think about when you use the Legendre series, right, you never, I mean, it wasn't, you could approximate a solution by cutting it off, but it wasn't something that that was eventually going to converge to a finite number. Now there's an alternate form to this, and that may be just as useful, or depending on what you're looking at. That is, if you look at successive terms, you can write this in terms of a quadratic. So n squared plus a to the 1, n plus a0 over n squared plus b1, n plus b0. And then if the idea is, depending on what you have for a series, if you can write it so it looks like this, use that. If you can write it in terms of this, use this form, the ratio of the quadratics. And for a1 minus b1 greater than 1, you have convergence. You have divergence when a1 minus b1 is less than or equal to 1. Okay. Now, I think it would be worthwhile to look over this again. Again, I'm going to post this on my YouTube channel, and there are some other examples in the text. But the Gauss's method is going to be really important again when we look at the series for these special functions. Thank you, series. Series, I get it now. Ah, that's why. Thank you, Siri. All right, we good to move on? Awesome. This is a good learning moment. All right. Great. So the last thing I want to do today, I think, is quickly go over alternating series. So what we've looked at so far are series in which everything is essentially constant, right? And generally speaking, monotonically decreasing. So for alternating series, these are, as it sounds, series in which they may be periodic periodically changing sign. Right, so we can, let's look at the Leibniz criterion first. So the Leibniz criterion for an alternating series looks at, again, is everything monotonically decreasing? And here we're considering the series from n to equals 1 to infinity of -1 to the n plus 1 times a sub n. Okay. And we're requiring a sub n greater than 0. Okay. So if it's decreasing, so monotonically decreasing, and the limit as n goes to infinity of a sub n is 0, then the series converges. Now, obviously, this isn't true for a series that has positive terms, all positive terms, but this is true for these alternating series. So we can consider the alternating harmonic series. So in this case, this is the sum is n equals 1 to infinity of -1 to the n minus 1 over n. And obviously that'll be 1 minus a half plus a third minus a fourth plus a fifth minus plus so on. Obviously these terms meet both criteria, so this converges. But it doesn't converge if we take the absolute value, right? And so this is pretty straightforward. And as long as we've got an alternating series that meets both of these criteria, we're fine. And we'll see some use for that, especially when we look at the algebra of series. It may be useful too to consider absolute convergence. So in the terms of absolute convergence, the definition is that the series u sub n is absolutely convergent if, and I know this is a shocker, that is convergent. Converges. Okay. You can have conditional convergence, which is what we have up here, if the series u sub n converges, but the series u sub n does not, right? So, for example, the alternating harmonic series is conditionally convergent, but obviously not absolutely convergent. Anybody know what's really interesting about the absolutely convergent series? And conditionally convergent series? And called Ramon's theorem, one of his theorems. Well, as you might suspect, when you have things that are adding, subtracting like this, you can, depending on where you stop that series, right? Your partial sum may be positive, negative, right? So conditionally convergent series can be made to converge to different values by rearranging the values. Right now, obviously, that doesn't work for an absolutely convergent series because it shouldn't matter how you add things, but if you consider the harmonic series, 1 minus 1/2 plus a third minus 1/4, right? We could write that as 1 minus 1/2 minus a third minus 1/4 minus 1/5 would be less than 1. Or we could group similar terms, say the odd terms, 1 plus a third plus 1/5 minus a half plus 1/7 plus 1/9 plus 1/11 plus 1/13 plus 1/15 minus a fourth, and so on. That converges to 3/2. In other words, if you look at how you're converging these series, you may be converging to a positive number or a negative number if they are conditionally convergent. And it depends on how you group these terms, which is not something that you can see with the absolutely convergent series. Okay, that is all I'm going to do for today. Since hopefully all of you, well, apart from Ben, got my email, and I'll send it again and make sure that the Moodle page is updated. The plan for this class is that we're going to meet from 10 to 11. I have my office hours, and then I'm going to supplement what we're doing here with a 10-minute or so, maybe 5 to 10-minute video example of something that we've talked about, just so that we're not sitting here for 70 minutes looking at a screen. So I'll do that and post it to the links to Moodle. And again, anything that I can do to help make this as good an experience as it can be, you should let me know. How was this for pace and for being able to see stuff? You can turn your mics on if you like. I want to hear your voices. I miss you guys.
It was good.
It was good. I thought it went well.
Okay, all right. Fantastic. So I'm going to let you go because you got to run off to your next class. I don't know. I haven't been to my office since I last saw you guys. So the coffee cup in there is potentially creating the solution to our nation's problems, depending on what's growing in it. So anyway, take care of yourselves. And if you have any problems, any situations, anything that you need to make this work better, or if there's something that happens at home that needs your attention, let me know, okay? All right. See you guys.
Bye.
Bye. All right, I have to stop sharing and all this stuff. All right. Okay. Bye.
Bye. Thanks, Meg.
Thank you.